our Physics Notes, Unit 2, Section 6, Refraction. This is part 2, in which we'll look at total internal reflection and critical angle. So we're going to begin by considering a semicircular glass block. And let's draw in a normal. This normal is going to go through the very centre of the flat side. So obviously we have air out here, and we have glass inside the block. Now we're going to send in a ray of light in such a way that it enters on the curved side, something like this, and hits the very centre of the flat side. Now, because it's entering at a right angle to the circumference there, then it travels straight through because it's lying on a normal. So there is no refraction at the first air glass boundary. We're really interested in what's happening at the second boundary, that's between the glass and the air. So effectively then, glass is going to be our first medium here, and air is our second medium. And that's important when we come to apply Snell's Law, as we will shortly. So this ray then will be refracted out. There's the straight through position. Remember, when you move from glass into air, you bend away from the normal. So you'd expect something, perhaps, like that to happen. And there's our refracted ray. Now let's imagine we send in a second ray. Same light, but just coming in at a bigger angle of incidence. So we've called that ray number 1, and there's where ray number 1 goes. Call this ray number 2. Where does ray number 2 go? Well, it's going to be refracted even further away from the normal than the previous one. Perhaps something like that. So there's ray number 2 coming out. Now, as you can see, as we gradually increase the angle of incidence, that would be the angle of incidence there, the angle of refraction gets bigger, there being the angle of refraction. And as the ray comes in at a bigger and bigger angle of incidence, there comes a point when the angle of refraction is so big that this happens. I'm going to change the colour of the ray on the diagram, but it's the same light, okay? So at some point, my angle of incidence will be such, like that, ray number 3, that my angle of refraction is now so big that my angle of refraction is in fact 90 degrees. And ray number 3 does that. Now that's a limiting case. We can't get any bigger angle of refraction than that. There is my angle of refraction. In fact, it's a right angle. Now when this happens, we say that the angle of incidence is called the critical angle. So there is the critical angle, and it's usually called theta c for critical. Let's define the critical angle then. So the critical angle is the angle of incidence for a ray of light in a denser medium for which the angle of refraction is 90 degrees. The critical angle is the angle of incidence for a ray of light in a denser medium for which the angle of refraction is 90 degrees. And that's the red coloured ray shown above. Notice that the critical angle does not involve total internal reflection. That comes next. It involves an angle of refraction of 90 degrees. Now, what would happen if we increased the angle of incidence even more? Well, that would mean doing something like this, having ray number 4 come in at an angle even greater than the critical angle. And what happens here is that in fact the ray is reflected off the flat side within the glass, internal to the glass, rather like it's a mirror. Like so. So that's ray 4. And when this happens, the angle of incidence equals the angle of reflection. And this is called total internal reflection. And total internal reflection occurs when the angle of incidence in the denser medium is greater than the critical angle. So, angle of incidence greater than critical angle. And you get reflection just like at a mirror as shown. Now, let's apply Snell's law and I should point out that this is a formal derivation which you should therefore memorize. You could, in theory, be asked to do this. So if we look at our situation, we're in the glass first, so that's medium 1, and we're in the air second, so that's medium 2. So we set up Snell's law then in the normal way. N2 over N1 is sine theta 1 over sine theta 2. Remember, medium 1 is here the glass, and medium 2 is here the air. Well, medium 2 is the air, so the refractive index of air can be taken as 1. N1 is therefore the refractive index of the glass. Theta 1 is the angle of incidence. Now at the critical angle, the angle of incidence is the critical angle, so that becomes sine theta critical. And theta 2 is, of course, 90 degrees in the air. So that's sine of 90. I'm going to drop the 1 next to the n now, because we know that the n refers to the glass. So 1 over n is sine of theta critical. Well, the sine of 90 is 1. So basically, what we're saying there is that n is 1 over sine theta critical. So for a given glass or other dense optical medium, the refractive index of the glass is equal to 1 over sine of the n is 1 over sine of the critical angle in the glass. So that is refractive index of the glass, or perspex, or whatever medium it is, and that of course is the critical angle within that glass. Okay, that is the formula and indeed the derivation which you should know by heart. Note of course that for total internal reflection to occur, the light must already be in the denser medium, in this case inside the glass, and the external medium is the less dense medium, the rarer one. It's called total internal reflection because you do get partial reflections for all of these 4 rays, but I've not showed those on the diagram just for clarity. Let's do an example. Glass has a refractive index of 1.5. What is the critical angle in this glass? So, the solution. Well, there's our equation. N is 1 over sine theta critical. So 1.50 is 1 over sine theta critical. So sine theta critical is 1 over 1.50. And theta critical is the inverse sine of 1 over 1.50. When you're calculating this, do it exactly as shown. Don't do any rounding prior to getting the theta critical calculated. Just type everything into the calculator and you'll find, only round at the last line, that the critical angle in this glass is about 42 degrees. Applications of total internal reflection. The most familiar one is optical fibers. These are used to transmit cable television, for example. And what happens here is that you have the optical fiber in a tube like that, and if you get the light into it so that the light is hitting the less dense medium at an angle bigger than the critical angle, you always get total internal reflection. So you get repeated total internal reflections all the way along, and the light travels through the fibre, trapped within it, if you like, undergoing repeated reflections, repeated total internal reflections. Because every time it hits the boundary between the optical fibre and the surrounding coating, and then ultimately there's air outside of it, you get total internal reflection all the time. If you're ever drawing these diagrams, remember the arrowheads. So you get total internal reflection there, and there, and there, and so on, and so forth. Just realised that that arrow is in the wrong place. There we are. So, that's one of the main applications of total internal reflection. And that brings us to the end of 2.6 refraction.